Okay, thank you for still being here. I can imagine that it's at least as hard for you to listen to 3 lectures in a row than for me to giving them. But anyway, I think I have still some hopefully interesting things to address. In the first 2 lectures, we have already heard about the problems we are faced with due to non-stationarity in time series. Non-stationarity in all its different forms, starting from trends over periodic components. And now we will address a second issue, which is also quite frequent, in particular in climate time series, but also in time series and any other field of research. And this is nonlinearity, and in connection with this, the emergence of scaling in time series. Okay, the methods we have discussed so far, autocorrelation function, power spectra, and so on, have been mainly based on the assumption that the underlying processes are stationary. And not only stationary, but also linear and stochastic. By linear, I mean that the processes are completely described by their power spectral density, by their probability distribution function, their power spectrum, and their correlation function. So these are the classical characteristics of linear time series. However, as I told you, typical time series are not necessarily linear. And it's the first question to address: how can we be sure whether a time series we are having for analysis is linear or is not linear? And the basic idea is, again, to formulate a null hypothesis for this statistical problem. And this null hypothesis, that our data come from a linear and stochastic process, can be quite efficiently tested by means of the method of surrogate data. Surrogate data are artificial data which are created in a way that they show the same linear features, so the same probability distribution function, the same correlation function, and the same power spectrum, like the original time series you have for analysis. But, and that's the point, the nonlinear features may be different. That's the idea. And if we have now some sort of statistics that is sensitive to detect these differences, we can just see whether or not our time series may be the result of a linear stochastic process or not. So that's the idea. So how can we create these surrogates? So there are, in principle, at least 3 different approaches. In fact, there are many, many more, but I think these 3 are most convenient, and you should understand them in a minute, as you have heard the first 2 lectures. So one is trying to estimate an autoregressive process for your data. Just to remind you, autoregressive process means that I can forecast the next value in my time series just by a linear combination of previous values plus maybe some noise. That's the idea. If we can describe our time series by such a process, it can be shown that the power spectrum, and that means also the correlation function, is quite well reproduced by this autoregressive process. Okay, this, as I said, gives us at least some approximate realization of the power spectrum. And by this, it's maybe the least valuable of the 3 methods. The second one is a bit more directly related to the time series. Again, I want to remind you to the previous lecture where I discussed the application of Fourier transforms to the analysis of time series. And what we can do now is the following. just please remind that the Fourier transform of a time series gives you a decomposition into amplitudes and phases. So let's suppose we have a time series, we make a Fourier transform, and then we have amplitudes for every single periodic component. That means every period nu we can have in this time series, and we also have the corresponding phase for every of these single periodic components. And now comes the point. When we consider this power spectrum, we have only made use of these amplitudes. So if we fix these amplitudes, we have completely fixed the power spectrum, and by this we have completely fixed the linear properties of our process. So the idea would be to take the inverse Fourier transform to get some realizations, and the inverse Fourier transform by using the original amplitudes but different phases. So that's the idea. So this method is called amplitude adjusted Fourier transform, or AAFT surrogates, and you can replace the phases in the Fourier transform signal either by random phases or, what is more convenient, by shuffled phases. So you take the phases for every value, for every period, and just mix them among each other, and then you have new phases which you combine with the amplitudes in the inverse Fourier transform to get a new signal, which has, again, the same power spectrum because the amplitudes of the Fourier transform are the same, but the phases are different. And by this, you just change the nonlinear properties of the system. Okay, that's the second one, and the third one is just when you have maybe non-stationarity in your time series, you know that Fourier transform might be a bit problematic to apply, but you can still do the same using wavelets and construct surrogate data by means of wavelet transforms. So that's maybe the three most important possibilities in applications. And if we have now these surrogate data which have the same linear properties but maybe different nonlinear properties, we need some distinctive statistics which allows us to understand whether or not these nonlinear properties are really relevant for our time series. And one example, so at least to my feeling it's maybe the easiest one, is the so-called time irreversibility statistics. Sorry, it's a very hard word even for a German tongue. And it's defined as follows. What you see in the denominator of this fraction is more or less the variance of a process. When you consider two different points in the process, you take the difference squared and take the mean value of this squared difference. And in the denominator, you have in principle the same, but not the second, but the third power. And as you know, the third power is sensitive to a change of these two arguments. So when I exchange these two arguments, I get a minus sign here. And that's why this statistics is called time irreversibility statistics, because it's just not time irreversible.